evening, everyone. Welcome to the data science program. We are in a module called machine learning, and under machine learning, we are looking at a particular machine learning algorithm that is called as the decision trees. Okay. So in the previous session, we had a detailed discussion on the theory part of the decision tree algorithm. So let us try to have a quick look at it, and then we'll come back to the programming aspect as well. So initially we had a comparison about what is the parametric model, and in machine learning some of the models are based on the parameters. So such models are called as the parametric models, and the learning process is referred to as the parametric learning. Okay, so that's the first thing we had discussed. So what are the various parameters that are going to be learned by the machines? If you try to recall, in case of a linear regression and the logistic regression, we had a parameter defined in the form of theta, correct? So this f theta of x comma theta is the representation of the learned model, and that theta will be the parameter which the machine is going to learn. So if you try to recall, after learning, the model predicts the value y cap by taking the given x values inputs in the form of x1, x2, x3, dot, dot, dot. So it's going to use the learned parameters theta. Theta actually is a vector, contains theta naught, theta 1, theta 2, etc. Right? And it will use this equation which you see here. Y cap is a predicted value. That predicted value comes from theta naught plus x1 theta 1 plus x2 theta 2 and so on. So that's the first thing. Right. In case of the parametric learning, irrespective of which model it is, many of the other models which are parametric models also we are going to see at a later stage. We will also see the non-parametric models, right, as and when required. So the one which we are considering right now is a decision tree. This is non-parametric model, wherein such parameters theta will not come into picture. Okay, so first we differentiated these. So what is a parametric model and what is a non-parametric model? The basic difference we saw. Okay, so after that, in case of the non-parametric models, right, we started with the decision tree. What are the characteristics? What are the basic features? It's a data driven, in the sense, looking at a data, machine is trying to learn something. So data driven, right? Then we are trying to optimize this model by using an algorithm that is called as CART, CART algorithm, which stands for classification regression trees. Now, as the name tree comes into picture, we should be able to recall something which we might have come across in any of the computer science related subjects, right? So maybe in algorithms or right any other subject, you definitely have even the data structures, right? The trees come. We might have studied the trees, right? So graph networks, etc., right, are a part of right from where the trees are derived. So our approach to learn the whole process was initially divided into 4 parts, right? So first we'll be looking at the commands. So that's what we have seen. Then we'll say that we'll be discussing about the visualization part, how a tree looks like. We'll be right learning that about that, how to visualize that. So once that is done, the prediction happens, right? And we'll be seeing the prediction mechanism. Then the maths behind the whole process. This is what was our approach. This approach was used to learn the whole concept of the decision trees. So initially I gave you the commands, right? Again, the commands were selected from a specific library called scikit-learn. So from the scikit-learn, you load a data set, you you import the decision tree classifier, load, right? And create an instance of your classifier and fit the classifier, etc. This is the procedure. Okay. Then we took an example of a specific data set, which is a iris data set that actually has three classes of flowers, and the classes of flowers are basically created based on four different parameters. So our X, that table has four different parameters. So what are the four different parameters? Sepal length, sepal width, petal length, petal width. Okay. So again, we could try to create a tree initially based on one of the parameters, which is the petal length. So it was an observed fact from the given data set. If at all it is less than 2.45, and if we check that parameter, if it is true, we say that we come to one side. If it is false, we go to the other side. Similarly, you can check another parameter, petal width, and true or based on true or false, you can create the tree in the following fashion. So that was what the visualization part of the tree. But in addition to that, we also have checked initially that what are the various parameters present inside a given node. So if you see, this is the node. One of the parameter will be checked over there. Most of the time, it will be true or false type of question. Okay. So here you see petal length is less than or equal to 2.45. Right? So the answer is yes or no, true or false. So such questions we ask. Then we have an impurity score called Gini score. Right? So the calculation we have done after this. Anyway, I'm going to touch that as well, just to make sure that you remember that. Then the samples, right? Then you have the values of samples and which class it is. So these were the five different parameters, each of the node that you encounter whenever you visualize or whenever you create this decision tree, we face them. Okay, so this was the next part which we have actually discussed. All right. After this, in the like that we had seen the various what do you call various depths of the decision tree. So in this case, the depth was defined 2 because starting from this is a root node. I have level 1 and I have level 2. So levels can be specified by us, right? So now once the visualization happens, we checked right how the machine actually tests, because the training part was discussed later. So initially, if you remember, we assumed that our model uh, is already trained. So we assume that model is already trained, model knows how to classify, and so we directly visualize the model, and then we did something like this. We did the testing part. So how it tests, take a petal length, petal width, something like that. So go and answer question one by one, starting from the root node. The root node said that is it less than 2.75, I guess, what was it? 2.45. So my first assumption was a sample with value equal to 2. So petal length less than 2.45, answer is yes. Directly come to the left, that is true, and your answer is class is setosa. So that particular data point is directly assigned to a class called as setosa. All right. So then we took another example. You can see that petal length is 3, petal width is 1. So right, the first question is false, so it comes to the right side. Then ask whether the petal width is less than 1.5. So the answer is 1 because answer was 1. So less than 1.75, answer is true. Again, you come to the left side and you said that okay, this is the class. Okay, so in that way the classification happens. So obviously one question comes into picture now. how do you decide which question to be asked at what node, right? That was our next approach. So in order to identify that, we had to move further. Okay, so this is just the explanation of the classification, right? You can see that we try to bring a term called as orthogonality. So the classes are orthogonal, 90 degrees, right? Each class is actually, right, something like that. This is what you understand from here. Then the mathematics came into picture before we do the training part. So that is called as the Gini score. For each of the node that we encounter in our tree, we have to calculate a particular parameter. Out of the 5 parameters in a node, this Gini is one of the score, and Gini is an impurity score. So how to calculate that and what does it represent, right? We understood that after we discussed the previous topic. So this actually, the Gini score is an impurity score. It is denoted by this equation. Whatever equation you see, Gi is equal to 1 minus summation k is 1 to n pik whole square. So the pik is basically representing what fraction of a particular class. We call it as a kth class. So first class, second class, third class, there are 3 classes. So k equal to 1, 2, 3. Right. In a particular node, what is the particular fraction of a class? What is the class of a particular, what's the fraction of a particular class? So first class has this much fraction, second class has another fraction, third class has a different fraction, and so on. So we calculate that p, square it, and take a sum. And that sum should be subtracted from 1. Right? So we took few examples over here. Just quickly try to analyze this. If you are able to recall, it's well and good. So if at all this is the representation of a node, what you see, Gini is given as 0.17, but just neglect that. So samples is 54, value equal to 49.5, right? So class is said to be a versicolor. Doesn't matter which class it is. Now, how do you calculate the Gini score of this one? It's 1 minus. So how do you identify which class what value it is? So you see here the first 0, whatever you see here, is the first class ratio. I need to calculate the I need to calculate the fraction by using 0 is the number out of 54 whole square. Then next one is 49 out of 54 whole square. Then the last one is 5 by 54 the whole square, because the last two classes have 49 and 5 elements. Okay, in this particular node. So use it, you get a value is equal to 0.168. Approximated that to 0.17, and I have written that. Okay, so this is how you calculate the Gini score. Just check if at all some other examples, you can check that the samples equal to 46. The values were given in this fashion. Okay, 0, 1, and 45. So if you calculate the Gini score, this comes to be 0.0434. Okay, and after that the sample values is changed to 100 out of 0, 50, 50. Now you see the Gini score comes to be 0.5. Right? So what, in the sense, in a particular node, right, we have several parameters present, out of which one of them was Gini score. We have calculated. What are the other entities, other elements present in a node, and it's to represent the characteristics of a node? You can see there is a particular parameter called samples, right? This actually represents the total number of training instances, right, for which that particular question you ask is applied. So first, initially you have all the samples present, so 150. So the first question was asked for all the 150 samples, out of which 50 said yes, 100 said no, right? So for the next layer, if you ask a question, there is the samples equal to just 100 because 50 are already out. So it's like that. Then the value represents how many training instances of each of the class wise you represent, something like a vector. Okay, something like an array. You see here the value equal to 0, 1, 45 inside the square brackets. Okay, so 0 for the first class, 1 for the second class, 45 for the third class. So that is what is represented. So this is how you do it. This is the meaning. Okay, then the class indicates the label, right, for which if you stop your questioning over there, what is the answer? Okay, answer will be said to be, okay, this is what is your class. Okay, so if you stop at that instance, any node, if you stop training or testing over there, the result will be like that. Okay, so then we discussed something more about the decision tree. Okay, so right, decision tree is actually a white box model. So we discuss about what is a black box, what is white box, etc. over there. And in case of a white box, we understood that everything is very clear. Why a particular decision has been taken for a given test sample, we will be knowing that, right, in a very clear fashion. We'll be having a clear cut answer saying that, okay, because of these reasons, a particular test sample is classified into this class. But that thing, right, may not be very clear when you study the neural networks, because the calculation happens under neural network in terms of some other parameters called weights and the biases. Okay, so you will not know why a input sample is classified into dog or cat category. Okay, so I know that, okay, this is dog, so it is dog. That not that part. What happened internally, and why the machine decided it to be dog? If you ask that question, answer is no, we don't. But here it is not that way. You can see that exactly this question is asked. So your data sample said belong to this. So it said no. Then I come to the second level. In the second level, the question asked was this. My data said yes. So the class is this. Like that, I can actually justify. I can see everything that happens inside the model. Okay. So because of that, it's called as a white box model. All right. Then, yeah, then we went inside what the important algorithm that is called as a cart algorithm. So cart algorithm is the training algorithm of the decision tree. So the procedure is like this. You start with a node. At each of the node, you will split the training data set into two subsets. Okay, so it's two subsets in the sense something which satisfies, something which does not satisfy. Yes or no type. Okay, based on what is the question? Because based in case of a testing, you know that, okay, this is the question to be asked. Okay, but during the training, this is a training algorithm. You have no idea what is the question to be asked. Now in the training, at what level of the decision tree, what question needs to be asked is what we are trying to find. Okay, so in that scenario, under that situation, so this is what you do. Look at the step number one. So go for a node, right? You try to split the data set into two parts based on two parameters. One, you select one of the features. Okay, take one features one by one. Start with x1, x2, x3, x4. If you have say 10 columns, you have x1, x2 up to x10. So for a feature xk, you need to decide a threshold. Okay, for everything, you see the petal length is greater than or equal to 2 point something. That 2 point something is a threshold. How did you decide? This is how the cart algorithm is the one which said that, okay, go for that x1, select the threshold as this. But initially you don't know about that. What do? You start one by one. Take x1, decide a threshold. Take x2, decide a threshold. Take x3, decide another threshold for that. So the calculation of tk part I'll come later. Okay, it's there in the next upcoming point. So for every for every x1, x2, x3, like the feature xk, you need to find out a threshold tk. So more than tk, one class, less than tk, the other class, like s or no. Okay, so this is what you are supposed to do. Now, how do you go to that xktk? Next step will answer that. A pair xktk for x1 2.45 is the threshold, for x2 1.5 is the threshold, for x3 something like that. So this is a pair, right? I need to find out, right, an entropy for that, right? How do you find out an entropy? This is the equation. So J is the entropy term, xktk is a pair, right? Again, tk is going to vary now. Initially, you start from x1, change your tk, start from the lowest value, go till the highest value, 0, 0 0.1, 0 0.2, 0 0.3, like that. Keep calculating this j value for a particular column. So I need to calculate the entropy using the equation m left divided by m into g left plus m right by m into g right. So what are these values, right? I think I have written that below. So you look at this particular diagram. We have xk like x1, x2. For that, we have to decide the threshold here. So what you do? Take threshold value 0 0.1, 0 0.2, 0 0.5, 0 0.9, 1.1, 1 point, like that. Keep changing. So when we go to the scikit-learn, it will does automatically. If you are writing a code, you need to take care of it. But anyway, we will never write this code from scratch. We'll definitely use the built-in one. But knowing the mathematics is what is important to us. What happens inside, if you know, that is more than sufficient. So for a given xk, change your t values, t1, t2, t3, t4, like that, like 0.1, 0.2, 0.5, etc. Keep increasing. Right. For every value, you get a left set, you get a right set, saying that something is true, something is false. Okay. So there are m total elements in when you ask a question, right? So m left is something which falls under true. M right is something, the number which falls to the right. Okay. So m left, m right. M is the total. So for each of them, you get a new layer, right? So you get a next layer. That particular node has some Gini calculated. So Gini left and Gini right. So though use them and substitute in the above equation, that is J. Every time you change your TK 0, 0 0.1, 0 0.2, 0 0.5, 0 0.8, 0 0.9, 1.1, 1.5, 2.5, etc. Everything you change. Okay. Out of for every value you get a J value. Okay. So which pair of xk and tk gave you the highest, right, is what you choose. Okay. So you see the next one. Continue the same for even the children nodes. I created starting from beginning, next node, node, and after that. So when do you stop? So you will stop when no further split is possible. Okay. Otherwise, right, in the sense the impurity of even every layer remains same means you have to stop. Okay. I created a layer. Next layer is also have to have the same level of same impurity. Gini score remains same means you stop. Okay, I have next layer, go to the layer next. All Gini score left means you don't have to do all this. Stop at the previous layer. Okay, so that's where it stops. Otherwise, you have another option. The user can specify, okay, I need only 2 layers. I need only 5 layers, like that. Okay, if either of the max depth is what is the parameter. So if you say max depth equal to 2, from the parent node, only 2 layers will be considered, layer 1 and layer 2. After that, it stops. So either max depth is reached or the impurities remain same even for the children node. Means you will stop. Okay. So that's the algorithm which actually trains the machine. So what is CART algorithm? How does it work? You know. In addition to that, you have what is called as a regularization. This was a new term which was coined over there, right? So most of the time in case of the machine learning algorithms, we see something, okay, that is uh, I think I had given the same example which I'm going to give now, just to make you understand. When I teach my students and during the teaching, if I ask a question, every question will be answered. Okay, perfect. So it means it suggests that, okay, whatever I am teaching, my students are understanding. Okay, so maybe after I teach students for 1 month and at the end of a month, I'll give a test. So, but unfortunately, during the test, though everybody has answered my questions during the class very neatly, very nicely, okay, but during the test, right, nobody is able to answer. Doesn't mean that I give a very difficult question. I say, let's say that I kept the same standard of questions which I had asked in the during the session, during the training session, right? But during the testing, right, result is not. Same thing will happen in the machine learning process as well, right? You train the machine, during the training you will do a validation, right? And the score corresponding to the training data set is very good, right? It shows a very good accuracy. It shows minimum error. Okay, but during the testing phase, what happens? Performance of machine is not good. During the training, if you see the accuracy 90-95%, very good. You say that, okay, training is very good. But during the testing, the same model which actually had given you 90 plus in the training phase, accuracy of 90 plus in the training phase, gives you 25-30% in the testing phase. Okay, so if you remember, the whole concept is what is called as overfitting. Okay, overfitting. Only that training data set what you have given, machine learns only that. Something comes out of it, it doesn't. Right, so that is what is a overfitting. So what you do, right? In order to avoid this overfitting, there are many aspects, many ways in which you can solve this problem. That is actually the general term in irrespective of which algorithm you use is called as a regularization. Right, regularization will help you out in reducing the overfitting of any algorithm. So this regularization can happen in various ways corresponding to individual algorithm. That's what is going to be taught to you in when we discuss various algorithms. That's for sure. But right now the overfitting comes in. If it happens, the regularization technique is called as the reducing the degrees of freedom. Okay, so user has to put a restriction on number of the degrees of freedom of the decision tree. So what are the various parameters using which I can specify, right, the degrees of freedom or the hyperparameters. So we have seen 5-6 terms over there. One is a maximum depth, minimum sample split, minimum sample leaf, right? The minimum weight fraction, etc. Many parameters we have seen here. These are the most common ones which the scikit-learn suggests us to tell the machine, saying that okay, I want you to train this particular data set using the decision tree, and when you do that, I want you to put these restrictions, use these hyperparameters with the value that I specify. I'm going to tell that to the machine, okay, by using the code. Then we also have seen what are the issues, something like a drawback. If at all you rotate your right data set, right, something like this, you see that the in order to maintain the orthogonality between the classes it is defining, it makes the data, it makes the decision boundary pretty much complicated, right? The technical term used here is convoluted. Okay, that's what you see in the screen. And because of this, if even if you make small changes in your data set, like moving a data point by a very small location, uh, the it may vary a lot of things inside your decision tree. Okay, so maybe it has to change the questions again. The top question may have to come down. There's a lot of changes are required for minute changes in the data set. So these two things are considered as the drawbacks of this. But yes, decision trees are pretty good. Okay, overall, if you compare, if I have say 10 different algorithms and I want to check which is pretty good, definitely decision tree will come at the top 2 or 3. Okay, again depends on what data set you are basically handling. You are trying to, what type of question you are trying to solve, that also matters. But in general, if I want to give you a general feedback about decision tree, it is one of the top. Okay, but yes, every algorithm will have its positive and negative. So while discussing that, I just mentioned these 2 points. Okay, so that was the theory part which we had discussed. All right, then we'll move to the coding part. Okay, so I'm going to run it on the Collab itself. So I expect you also to run on the Collab, but yes, definitely you can run it even in your system, right? Irrespective of where you run, we'll be getting the similar results. All right, so let's start. First, let me connect. Okay, it's connected, and I'll install the D3Viz. It's a library which is used to visualize the decision tree. So D3Viz, as the name suggests, you are trying to uh, visualize that. Okay, so then numpy. Bring the pyplot from matplotlib. Okay, then sklearn import the data sets are available inside this, so you can simply bring it in. Okay, so data sets are present, and then we'll bring in the tree from the sklearn. Dot tree. Decision tree classifier, then import graph viz from dtree dot trees, import dtree. Okay, now the initial few steps are maybe common to what we already have done, but I want you to recall the whole procedure, so I'm not using the same file which is already existing with us. I'm writing it once again. Okay, so the first thing is we load the data set. Okay, I'll call it as iris equal to datasets dot load iris. That's defined. So x is equal to iris dot data, and I'm going to restrict to second till all from the second column onwards. Okay, because first two columns I'll remove. I don't consider. I'm taking only the second because I want to show that I want to show the exact diagram which I considered in the discussion when we had a theoretical. Okay, so that's why it is iris dot data, then iris not iris, sorry, we'll go for a y value that is equal to iris dot target. So if you look at the iris after you load, it is actually it's going to contain two arrays. One array is complete data, second array contains target. Oh, my mistake, sorry, it's just a colon, right? Data colon comma. Okay, let's see. All right, so I mean if you check iris, you will see that there are two different arrays. So array number one says the heading data, and the array number two is target. So the complete target becomes y. So in the first one, I'm considering right? See, this is column number 0, 1, 2, 3. So 2 onwards. So 2 and 3 are considered. So in the next one also 2 and 3, 2 and 3, like that. Okay. So that's what we are doing in the previous step. Right. Now, anyway, I'm not going to use it in the actual code. So let me try to define a function. So classification function, short form is CLF. It's decision tree classifier. I can specify, right, the maximum depth that is required by using a parameter that's called as max underscore depth equal to. So you can say that I just want 2. Okay. And there is one more thing. If you remember the theory concept we had discussed earlier, I think I have mentioned a particular point that uh, since the data is fed into the card algorithm at a random fashion, maybe the tree that you are going to get keeps on changing. Okay, every time you plot, right, the tree will change, but ultimate result, ultimate classification has it will not be affected. So, but the plot will give you different trees, right? To avoid that, it is better to specify a particular randomness, right? So by using a random state. So I'll define random state equal to, give a number, but stick to that through. Okay, maybe 100. So that is the CLF, and the model is equal to, use the fit function, pass the x to this and y, x and y, I am asking the machine to fit. Okay, so the machine fits. Right. So my first objective is to have a visualization, right? Have a simple visualization that will be done by using export text function. All right. So we'll see that first. Okay. So I'll call it as the text underscore text representation, that is equal to, in the tree, under the tree, you can specify that as export underscore text of your function that is called as CLF, the classification function, and I want to display the result, so I'll just call print. It's a text format, so you can simply call the print. Okay, it's a text representation. So we can see, right, the model which has been created now, right? I can simply see in the form of a text. That's what is the result of this particular cell. Okay. All right. What I do, I'll share this particular document for your reference. All right. So let me copy the link and I'll paste it in the chat box so that everybody can access the same file. Right. Make a copy in your system or on your system, and you can keep accessing that as soon as it gets saved on my side, right? The most recent version of whatever we have here, you can access that. Okay, so don't type, when you click the link, something opens, right? Don't type over there. That actually conflicts whatever I'm typing and whatever you type. Okay, so please don't do that. I expect you to make a copy of this, whatever opens here, save as, go to the files and right, save a copy in your drive. When you click on save a copy in drive, right, it will get saved inside your drive in your name. Okay, so that one you can type. All right, you use this link only to access what I'm typing. So you can copy from here and paste it in your file, it will run. Okay, fine. Right, the most recent copy, so up to 7 cells have been typed and you can access that. All right, moving ahead, I think we discussed about the saving this particular file in the form of a picture format. So I'll show you that. So in order to write it into a figure, right? If you remember, you need to create a file by using a file handler, give some permission to write the file, and just call a function that writes the file. Okay, so I think I gave an example of a figure. So you use with, you have to say open something. So open which particular uh, file you want to write. Right? So that will be maybe I think I called DT decision tree dot. You can write in any format. So I will open a log file. Okay, dt.log, and specify, give a permission to write. W for write, R for read if you are reading something. So as f, let's say now f out, that's a file handler, dot, it's a write function. Okay, I'll say, what's the name, text representation, right? Okay, so just check that before I write, these are my folder. This is what is there in my my computer. So my system has, right, only one folder called sample data. Okay, now I'll run this. Okay, it said it is running. Now if you check, you see the one which I asked, dt.log, that actually came here. So in a sense, you can write a file in this fashion. Okay, so that's the first objective, right? How do you write, to save something which is created already by yourself in the decision tree visualization? You can save it. This is one option of saving a file. And if you remember, the next option under the visualization is to use a function. Okay, so what I do, I create a figure that is equal to plt dot figure. So you will specify a size. Okay, that is fig size equal to, specify some size, maybe I'll write 10 comma 10. Okay, so that's the size of the figure, and I will call the plot function under the tree dot plot tree. I just have to specify the function, that's a classification function, then feature names. Okay, what are the feature names that you want to give? In the inside the iris, use feature names. Okay, then what are the class names? So class names have to be, once again, in the iris data, use target names. And so do you want it to be, I think this is the option for coloring. So fill equal to true. So you should be PLT. Yes, plot and sorry, not mistake. This is PLT. Okay, so as you can see on the screen, right, we have the same decision tree printed, like we have used the one with the two maximum depth equal to 2 in our theory case. Okay, so even the values are calculated. This is why I took the same example as what we did earlier, because we should be able to visualize what we have discussed in the theory part on the practical side as well. Okay, so I think this is pretty much straightforward. Okay, then I'll go, okay, let me save it so that you can access it.
Is some rolled down?
Yes, Somesh. What's the
Yes,
question?
please थोड़ा सर थोड़ा सा ऊपर करिए कोड जहाँ पे.
Yeah.
Okay.
Okay, sure.
Thank you, sir.
Sure. You can access the same code from the file link which I have shared. Okay, so it's saved there. You can, if you open that, it will come.
Yes, sir. Yes.
Sure. Okay, so till here, fine, I guess, right? Do you have any doubt? Anything you want to explain again? Please go ahead. You can ask anytime. All right. Let's let's move ahead. Let us try to save this, right? So whatever visualization we have here, right? I want to save that. So in order to save it, simply go for use the figure name, that is figure handle fig dot use a function called save fig. Yeah, okay. We have save fig. Just give a name. Okay, my decision tree dot png jpeg many other tiff many formats are available, left to you which one, right? So already we have discussed the various file formats that are supported in the matplotlib itself. Okay, just go back, check there what are the options you have, and you can simply save it in that. Okay, right. Then the next option is we will try to uh, ask the machine to give me a probability, right? Because each class will have a classification probability associated with that. Let's try to let's try to give it. Okay, let's try to ask it. So in the CLF, in the classification function that has been learned by the machine, right? I'm going to ask, give me the it's a predict. What's the function? Predict probability. Yeah, predict probability of. So I will specify, it has to be entered in the form of a list itself. So 5 comma 1.5. Okay, if at all my data is 5 comma 1.5, what are the chances of this belonging to class 0, this belonging to class 1, this belonging to class 2? This is my question. So you see, it says there is no chance that it belongs to class, your first class, Setosa. There is 90% chance that this belongs to the second class. Okay, and there is just approximately 10% chance that this belongs to the class 3. So what do you expect? This particular data set actually belongs to class 2. All right, so let's see whether the machine classifies the same thing. ELF dot I'll call a predict function, and again I'm going to pass the same thing. So this is how much? What was the number? 1 5 comma 1.5. So see, it is 1. 1 indicates this is class 0, class 1, and class 2. Okay, so this actually says class 1. Okay, let me save this. Okay, it is saved. You can access the code till this cell number 40. All right, and then coming back to the theory part, in the same flow, we are writing the code here. After this, we went into the cart algorithm. We looked at the steps involved in the cart. That's already implemented here because we have created the decision tree. We call the decision tree function, and we call the fit function. Fit actually does the same thing. Okay, so it's done. We don't have to write any code for that. And after the learning is complete, we looked at what is called as the regularization, right? So let's look at that aspect now. So regularization of the hyperparameters are what, right? We have to, right, see. Okay, so let us try to write a code for that. Okay, so this is the regularization part that's going to be coming now. So once again, I have the okay, let me define the iris once again. Okay, let me say that this is a regularization, so that when you read it, you will understand. Okay, so this is the regularization part. So first, let me bring in the iris once again. I think it is already loaded. You can, even if you copy and paste same thing, it should work. Okay. The data sets dot load iris. I will define the x value, that is equal to iris. In the iris, go to the data and all these rows, second till the end, and y is equal to iris dot target. Okay, till here we already have it. Now first let me define the decision tree classifier without specifying any of the hyperparameters. All right, so that is CLF1. So this is equal to decision tree classifier. Don't even specify the depth, though you know that depth can be specified to 2. Don't specify, because the depth is a hyperparameter. All right, so I'll not specify anything. Simply I'll just define a random state. Okay, random state equal to, so maybe some number you give. I think we gave 100 earlier. I'll stick to the same thing. Okay, then tree, is it tree? Sorry, what is that? CLF1 dot fit x comma y. This fits the CLF1 decision tree classifier. No hyperparameters are specified. Okay, that's the first thing. And now I should be able to do the same thing. I should be able to repeat the same thing, but but with the specification of the various hyperparameters. So let me try to show you like this. So I'll call it as CLF2. Okay, so that is equal to, again, the decision tree classifier. I'll specify. So what are the various hyperparameters that I want to use? I want to start with the maximum depth. Max depth, specify that equal to 2. I'll keep it 2. And right, the minimum samples leave, right, that is equal to 1 once again. And I'll specify min split. Okay, so I'll try to keep that as 2. Right, even when there are 2 samples, I want machine to split it. Okay, then random state, keep it same. All right, so that's the specification. Now I'll go to the CLF2 dot fit with the same data x comma y. Okay, let me check. Will you have any error? No. Okay, so that runs. So the regularization is actually happening in this part of the code. Okay, but in order to visualize, I have to call. It's not a straightforward method, right? I will call a function. Okay, I'll write a function here. Let's define plot the decision boundary. So that's my function. All right, and I will pass what is the function, what's the model, right, which is the classification model that we built. So that is what I pass first. Then I'll also pass x value, then the y value. Okay. Then you can set to what axis you want if you prefer. So axis equal to, so start from 0, go till this is the width, so 7.5, 0, comma 3. Okay, so let me pass this. These values will be passed to the function. So let us try to create the axis first. I'll call this is x1s is equal to, use numpy np dot linspace axis of 0. Starting from there, axis AXES, right? Axis of 1, and I want to create 100. All right, so 0 to 7.5, that's again you're taking that as one of the axis. So creating 100 samples between 0 to 7.5. Next, create the second one, x2. This is equal to np dot linspace. So I'll go to the AXES, the next element, third element, denoted by index 2, then axis, index 3, again create 100. Okay, then what I do, I'll create x1 comma x2 is equal to, create a grid out of it. All right, so that is it mesh grid? I think it should be numpy np dot mesh grid. Yeah, np dot mesh grid of x1 and x2. So we create a grid so that on the grid you can plot something. All right, so that's, if you remember the 2D plots we considered under the matplotlib or even the cboard, right? This similar concept was used, right? We are simply replicating that. Okay. Right now, in the next step, what we are trying to do here is that we get a new x values and the y value, right? Because so many x values are created, right? And so many y values are created. So you see here, what this numbers stand for, 0 to 7.5 is one of my parameters from the data set. If you observe carefully, the petal length varies from 0 to approximately 6 point something. So I created 7.5. So 0 to 7.5, I create all the numbers. Okay, and the petal, one is petal length, and another one is petal width. So petal width we specified one value, petal length will be actually from 0 to 3. So that's the range which you find in the data. Okay, so that's why these numbers are specifically created. So if you ask a question why 0 to 7.5, it's from the data set. So I can see that the data varies in this particular range. Okay, and the next column has a values from 0.5 to 2 point something. So we create 0 to 3. Okay, that's the only reason. Create a grid out of it, right? X and y, right? One is along one axis, other one along other axis. We want to mark the points over there, right? So this is what is our ultimate goal. Now what I do, I create X samples at random. Corresponding to X sample, I create a Y sample, because for every value in X, I will need a value in Y, so that X comma Y is a point which is going to be marked over. All right. So let's try to write that. So there is a function called ravel function. All right. So if you remember, we had used the ravel function once again. If you need a help, you go to the help and check out what it does. All right. So I create X new is equal to np dot c, right? I will create the x1 dot RAVEL. It's a function to create the new values selected from x1 and x2. All right. So x2 also do the same thing. x2 dot. All right. So that's a list that is getting created, and predict the y values. Y predicted is equal to use the CLF, the function dot predict, which is your test data. In right now, the x new is the data. Okay, x new. I'll pass. Then I will try to perform the reshape, because it has to be in the same shape as one of your data sets. So x1 dot k. So I have a data points available, because my intention was to plot something and see the decision boundaries. This is what is my case, and how we understood that because of not having a regularization and having a regularization, I want to see a proper difference. If you don't do regularization, what happens? If you do regularization, what happens with the decision boundary? So that's why I'm writing a function for plotting the decision boundaries. I'll call this function twice. One without regularization, one with regularization, so that the what do you call, difference becomes very clear to you. Is that okay? So that's my idea here. So I will bring the color map into picture. Okay, so custom C map. So custom color map is equal to, it's actually already we have loaded that. Okay, so listed color COLOR. Okay, listed color map. So you have an option to specify the various colors that you want to see on the screen, right? So now you see I'm going to specify 3 colors over here, right? Each color corresponds to a color. Each representation is a color actually. Okay, again, I'm actually copying from internet itself. So let me just copy them and paste it over here. So 3 colors I'm bringing in, one for light yellow color, light blue color, light green color. Okay, so those are the 3 things, right? Again, you have various representation possible. If you go back to the basics of colors we discussed in Matplotlib, you get the details of this number. That I have given a short notes in the material which I have given to you, that okay, what's the representation for which color? Okay, red, most of the standard colors I have given a code. Okay, you can refer that. Right, you want to modify this, you can go, you can search in the website, and which color you want, you can just do. All right, so that's the color map is that's what is a color map is going to do. Then the plot, get me the contour plot, CONTOUF of for x1, x2 is the second data, y predicted is the next data. Okay, x1, x2 and this, and C map is equal to the custom C map. Okay, so the colors are provided now. I will say that right, what are the various colors that I want to bring in for the plots. Okay, so if I take a data from say the Setosa class, I want to give it a yellow color. All right, so plt dot plot x. So plot should be x comma y. One is what is along x axis, what is along y axis. Okay, so I have to say that only for the data points which belong to my first class, that is the Setosa class, I want to give a yellow color. Okay, how do I specify? This is how you do. X is my data, right? All the rows, and the zeroth column, right? Because I have only two columns now. First column indexed by 0, second column indexed by 1. So go to the 0, and the condition is that it should belong to which class? Y equal to 0. Y equal to 0 means output equal to 0 class. That is a setosa class. Okay, again you can observe this from the data set itself. Okay, so that is my x value, and go to the same x, take up all the rows from the first column, zeroth column first. Okay, so I have to have a condition that select x1 and x2 in such a way that they belong to class 0. Only those you put a yellow color. Okay, so x of all the rows, zeroth column, y equal to 0, comma, x of all the rows, first column, again y equal to 0. Okay, this is not the only way to write the code. You can do this using maybe any other conditions like if else or any other format that you want. Okay, that's also possible, but I'm trying to keep it simple so that when you see, you should understand. Okay, this is my data point, and you can specify, give me yellow colored LOYO. So yellow colored circles, give me for this. All right, and I also want a label. So give me a label equal to setosa. So that's the first color that I'm specifying. Then ELT dot plot, pretty much it will remain same like the previous one. Okay. So that is x of all the rows, comma, 0th column. But now you see I'm going for a different class. So y equal to 1, my next class. Okay, so that will be the vertical plot, vertical class. Again, x of all the rows, first column, and y equal to 1. Now change it. Let's say I think I had given the same blue colored squares. BS stands for the square. Give a label that is equal to what's the class? That's the next one. ELT dot plot all the rows, 0th column, such a way that y equal to 2, my first point, again x of all the rows, first column, specify that y should be equal to 2. Let me specify a different color. I think I had given green and triangle. Okay, right, give a label, equal to Virginica. Plot no, PLT dot axis axis. So that actually plots with a specified marker and a specified color. Now the next objective now is to plot the x label. X label, so that is sepal length, y label, sepal width. Okay, Okay, then go to the legend part. Right, legend. Give a specification. Okay, so location equal to lower right. You can specify any other location as required. Okay, so that's the plotting part. Now let's call this function ELT figure fixed size equal to maybe 10, 10. What's the name? Plot decision boundary. Right? Pass the function that is right. The first one ELF1 x y. All right. Then let's see what happens. So you can see that this is the decision boundary, right? Whenever there is no regularization. So CLF1, if you see, what is the CLF1 defined? Can you check here? Where is that? Yeah, see CLF1 is here, right? In the CLF1, I don't see any hyperparameter being specified. But CLF2 is with the hyperparameters such as max depth, min sample leaf, min sample split, etc. Many out of the 6 different things we discussed in the theory side, we have just implemented 2 or 3 here, right? You can definitely implement others. Okay, so this is what happened. This is what is the decision boundary you get when no hyperparameters are used. Simply you left the decision tree free, right? It can decide that whatever it is. So you can see this is how it came. Now, let me do the same thing again. ELT dot. Okay, first let's create a figure. Figure of fixed size equal to 10, 10, and I'll call the same function once again. Plot the decision boundary CLF2, right? Now with the regularization, okay, terms, and pass the same training and the pass the data set and required y value. Okay. So this is a very clear-cut boundary defined, right? We were expecting the proper decision boundary in terms of they have to be what you call orthogonal. So that was not a case here, right? Right. It didn't basically satisfy the condition, right? That's what, because of this part. Okay, we were expecting either this line to be extended vertically or this horizontal line to be extended, but that none of them happened. But here you see it's pretty much proper. Okay, so here you see it is actually learning all the given training data. What are the training data? You see training data in the sense the blue colored dots or the yellow colored triangles are the training data. It tries to learn that perfectly. That's all. Whenever a new sample comes somewhere outside this, it has no idea what to do. That's what is overfit, right? So see, but here you see anything that comes below this line, even on the right side, right, it will take care. It will say that, okay, that belongs to this class. Okay, anything above this horizontal line, it will tell that it is, right, that particular class. right? So again, maybe you will do mistakes. Mistakes are fine, right? I'm not a, nobody can expect a 100% accuracy in that. Here you see it tries to do the 100% accuracy, but actually in the testing phase it fails. Okay, but here it is not that. You see the decision boundaries is pretty much right, straightforward. Right, anything that below this, that falls below this is a class vesicular. Anything that goes above that is clearly a virgin. Okay, so that's what is the significance of what we call as the regularization, and it is very important. Okay, right. Now, very similar to this, I'll try to touch another part of the algorithm that is called as the decision tree regression. Right, we can even do the regression using decision tree. Right, so since we have already done one regression problem and one classification algorithm, so it becomes easy for you to understand what is happening in, even on the regression side. Okay, so let's go with the coding part of that. All right, so far any doubt? Let me save it so that you all have access to this. Okay, it's saved. So till here everything gets saved, so you can use it if required. Okay, so any doubt with this? Okay, okay, the next concept which we will discuss in the theory, we have not discussed in the theory side, but anyway the implementation is pretty straightforward, pretty simple, so that you can understand what is happening in the regression part. Okay, so let me get a data set. Again, this is a Boston. I'll got as a Boston, right? From the data set, it's present in the form load the load Boston. Okay, so x is equal to Boston dot data, and y is equal to Boston dot target. Okay, let's inspect data set. What's my mistake? Data sets. Sorry, it's data sets. Okay. Yes. All right. So data sets we have. Let's check what is in X. Right. X is, you can see list of list. All right. Again, I can check what is there in Y. I'm expecting Y to be a continuous variable so that you can do a regression. You can see no classes are defined. Not like 0, 1, 2, 3, or not just some classes. It's a continuous variable starting from some minimum to some maximum. So this problem becomes a regression problem. I will show you what are the feature names. Boston dot, okay, feature names. Okay, so various columns are there. Each column has been given some name. Okay, right? It is this data set is directly available inside the sklearn package, so directly we can implement, we can bring it. So based on these many parameters, okay, a y value is given, which is a continuous variable, which means we need to predict, okay, that value. So this becomes a regression problem. Okay, right. Now what we do, will create a regression. Okay, I think we need a regressor to be present. Okay, let's import, because we have not imported the decision tree regressor for our case, right? So it becomes absolutely necessary to bring a regressor. So let's load that. Okay, from sklearn dot tree import decision tree regression. So classification algorithms cannot do the regression, right? So regression needs a different import. Okay, so we'll bring in the decision tree regressor for this purpose. Okay, so let me call a decision tree is equal to decision tree regressor of define. I'd like to maybe the max depth equal to maybe again we can change this. All right, it doesn't work if it's not very accurate. Definitely you can change. All right, randomly I'm going to put this number and go for a go to a random stage, put a number so that every time you get the same. Okay, and go to create a model that is equal to the decision tree dot fit x comma y. All right, so once the model is fit, definitely I would like to see that. So visualization comes into picture. All right, let's go for the similar visualization that we had earlier. Okay, so that is text representation is equal to tree dot export text of the decision tree, then print it out. See, so what you can conclude from this? It's a very similar thing, right? Regression and the classification. If you try to remember the linear regression and the logistic regression, whatever difference you had, right? Very similar approach over here. Okay. We can visualize and you see that it generates the tree in a pretty much similar fashion. It chooses the appropriate feature and a threshold, right? Comes down to the next level, specific feature and a level. You can see the levels that you are getting over here are completely different for them. Only the first question remains same, less than or equal to this, right? So it is yes means you will come inside. Yes. So if this is yes, you will come inside. Okay. And so on. So that's one type of visualization. Let me save it. Okay, so this has been saved now. You can access still here. Okay, so let's take a 20-minute tea break.
Sir, one confusion.
Yes, so much. Please go ahead.
Yeah, sorry, I
No
am
problem.
missing the last 4-5 classes. I am missing. I am surveying in the field, data collection. So I
Okay.
have not attended the last 4-5 classes.
Okay,
Regularisation.
No
So,
problem.
sir, can you use Collab in the Google? Yeah, first I have download, setup and then install.
No need
laptops
to download anything. Okay, no need to
Yes, sir.
installation, right?
Yes.
So what you have to do in order to use a Collab, simply
Yes, sir.
go to your web browser, click on
Yes.
new tab. So now I clicked, I'm using Microsoft this thing. Okay.
Yes, sir.
So it opens something, right? So go to, right, simply go to the Google. All right. And simply type Collab, right? So you can see Collab. So Google Collab comes into picture, right? Just
Yes.
click on that, right? It will ask you, right, to open a new thing. So I have been using things long, so it's this what I already opened. Okay, so many things are there. I want you to go to a new notebook. Simply click on the new
Okay.
notebook, empty file comes,
Yes.
start typing over there. That's all.
Okay. Okay. Thank you, sir.
Sure, sure. Any other
Hello, sir.
doubt?
Hello, sir.
Yeah, please go ahead, Devendra.
Yeah, sir. Same code we can do with Jupyter also, no?
Yes, definitely. This works even on Jupyter. Okay.
Yeah. Okay.
So no difference. It's the same Python, same platform. Only the difference between the Collab and the Jupyter is that Jupyter runs on your system, Collab runs on Google's server. That's all.
Okay.
Okay.
Sir, you have used the data also. You have shared a file last time.
For this particular code, dataset is not required. Okay, dataset is there built in. So you see here, I actually, I'll go to the top. So you see here, the data sets are actually imported from the sklearn. Scikit-learn has the data sets which we are using. Okay. But if I am using some data set which is not present inside this, I have to give it to you. Okay. In such cases, always I'll give it that I'll give that particular file through the chat box. Okay. Right now it is not required. So directly just write this line of code. It means that all the data sets that the scikit-learn has is made available to you. Okay. Directly you can use it. So simply say that datasets dot iris data comes into the memory. So for a regression problem, I loaded the other file, which is a Boston file. So just see here, datasets dot load Boston. So that particular file, complete data comes into the memory and it will be loaded into the Boston.
Yes.
Okay.
Okay. Thank you, sir.
Sure. Any other doubt? All right. So please take a break of 20 minutes and come back. We'll resume from here. Welcome back, everyone. Sorry for the inconvenience. There was some technical issue because of which the meeting got ended automatically. So we were in the middle of the regression, and the decision tree based regression is what we were looking at. And the coding part was half done, and we loaded the Boston dataset from the scikit-learn, and we imported the decision tree regressor. We created a model by fitting that, and we visualized. Okay, so far this is what happened. And next, let's try to visualize using a different library. So for regression, the visualization of the regression happens through a library that is called as a graphical visualization. Okay, so let's first import that. Import GraphVis. All right. So this is a tool which is used for visualization of the regression trees. All right. So one option is by using the text method, which you see on the screen, right? The second method is what we are trying to implement now. So let me create a figure now. Is equal to plt dot, it's a figure, specify the size. So peak size is equal to 10. Let me define like this. Then tree dot, sorry, not figure, my mistake. Plot the tree. I think we have already a decision tree with us. That is that's DT. All right. So I'm using the same thing. You just have to pass what's the name given to the classification or regression function. So that is DT, and I have to specify the feature. Okay. Feature names equal to, it's a Boston data set, so I have given name as Boston itself dot feature names. I want the coloring, so fill equal to true. Oh, my mistake. True is Boolean. In Python, Boolean is capital, right? Capital true. You can see the complete tree getting displayed over here. So the various names of the parameters are what you see over there on the top, right? Then instead of the Gini, right, you are actually calculating the squared error and the samples and the values, right? So you see that's a difference between the regression problem and the classification problem. Okay, so if you actually remove this part, right, I think we don't get a color. Yeah, no coloring if you remove that part. Okay, so just to get a coloring option, normally we try to say filled equal to, okay, that's the second option, and I'll show you the third option. So in the next option, I'll create my data is equal to p dot, there is a function called export yeah, graph list. I have to tell which is the file or which is the CLF, that's a function. Then do you need an output file? Do you want to write it to something? It's a question. So if you don't want, you simply say that no, I don't want. Okay, so out underscore file, yeah, out file equal to none. That's the second thing. Then the feature names should be specified. Yes, you have. Feature names equal to, again the same thing. Go to the data set with the name Boston. Feature names. Okay, and what else? Yeah, we'll go for filled equal to, so that you get some colors. Okay, and we'll also do graph width dot source of my data format equal to PNG. Okay, I want to save it with this. Okay, let's see what happens now. So see, the graph is actually right, gives you a much better view of that. So it's actually pretty big. Okay, so again the decision tree itself, right? Various parameters are what have been compared over here. So to the left side, if you move, it is true. If you move to the right from any node, it is false. Right? So the final nodes, right? That is the last nodes are not going to have any questions to be asked, because that actually is a value which will be predicted. The value predicted will be 45, value predicted is 22, and so on. So this is what it learns from the whole data. See, this my dt is also saved in the form of PNG. That's because of my last command. All right, I'll show you. So the last command is that, right, create a file, right? So this is the function source of, okay, whatever you have, right? Make this, that is my data, in the particular format told as PNG. You can save it using other methods as well. So that's another technique, that's another method to visualize the decision tree using graph base. Okay, let me save this. Okay, so you have the link available, and the same link you can use it to access this particular file. All right, then again the d3 viz is already there, already we have used it. Let me try to show that. Okay, so that is viz equal to d3 viz. Decision tree is dt x y and target name, yeah, target name equal to target. This is present in the data set, right? And feature names to be equal to the Boston dot feature names. Okay, so now you can see this the similar plot in terms of the data points. Okay, this is another view. So originally you had that complete cluster what you see over here. Okay, but later on it is divided into two parts, right? One like this and one more like this, based on your the parameter, which is LST80. So whatever column it is, based on that it is divided. Then you see it is further divided divided, right, into two more classes. Okay, two more subcategories. Then those are further divided. You can see it's a level below. So out of this data, this complete cluster, what you see over here, right? It has been classified in the sense you are actually making a regression here. It's not a classification, right? So the leaf nodes are at the bottom. So visualization is different, that's all. Okay, same thing as this. So instead of see DIS, right, writing there, you see the DIS, right, data points marked over here. Okay, so that's the usage. Okay, let me save this. All right, let's go further, right? And now I want to plot, right? I want to define a function that actually plots the predicted values. All right, so define plot predictions. I will pass the tree regression. That's a model. I'll pass the input features and the target values. And I'll also pass, say, access equal to. So it again, this has been observed from the given data set itself. So the minimum value of one of the parameter is 0.3 and the maximum value was observed is 1. Okay, close to 1.95 also. And the second parameter where is say 0 to 60. All right. Okay. Let's define. Create x1 is equal to np dot linear space. Go to access. The first one, index is 0. Access, index 1. Let's create 500 samples. Reshape. All right, then go to the prediction now. Y predicted is equal to, go to the function. The function we are passing it as the regression tree. Okay, use that dot predict of the sample which we have created, that is x1. For every x1 there will be a y that is predicted now. Okay, so once this is done, go to the plt dot axis of this axis, then plot plt dot go to x label. X1. plt dot y label 1. plt dot plot. I'm going to pass, this is my x value, this is the y value, and I want the format of plot, the data points should be marked by let me say blue colored dots. Let's see what happens now. Okay, and I'll close this. Then plt dot plot the x1. X1 is newly created data, and the y predicted are the corresponding predicted value. Both we are expecting them to match. Okay, so let me give a different color, say red color, and I want dot dash. Let's see. Okay. All right. Let's. So I will call only a part of my data set now, because if you look at the X, that is a Boston data. Can you visualize that? Is it possible to visualize on a graph? Can anybody try to answer that? Because you know what is our data set, right? So I'll show you the data set once again. So see, this is X. Okay, you can look at the size of the data set if you want, right? But my question is that if I get the data set, what you see here, right? in this particular cell number 21, right? Can you visualize that? Is it possible to bring a graph and see that? Is my question. Any type of graph, can you visualize that? Only yes or no type of answer. The x, what you see here, is what is the dimension of this signal? Dimension in the sense how many number of columns you have. Okay, so you can count. If it is more than 3, definitely you cannot see. Human interpretation is not possible. So because we can perceive the 3 dimensions max. So in a 3-dimensional space, I can plot something and I can understand. But 4th dimension means how it will be, I don't know. I know that there is 4 dimension, 3, 5 dimension, 6, 7, 10, 100, 1000, etc. But the problem is that visualization, interpretation through human brain is too difficult. Okay, so because of that reason, what we are trying to plot here is only a 2-dimension case. Okay, so you see, I'm actually taking only 2 of the values, 0.3 to 1, and another parameter from 0 to 60. Okay, only you can see axes have been created with only 2, right? So only 2. The x which I pass here should be of only 2 dimension. So what I do now, I'll create that. So x is equal to from the Boston data set. What is that? Boston dot data, right? Read all the rows, but the specific columns, 4th column to the 5th. Okay. I'm going to read only that. And y is equal to, it will remain same. The Boston dot target. Okay, I hope you understood why we are doing this step. We are not taking the complete data because of the restriction of visualization. What we can see, there is a restriction on. Okay, so the next part is we'll call, say, I'll call it as DT1, like we did earlier, with and without regularization. Okay, I don't define any hyperparameters for the first time, and the second time when I define DT2, I'll create that as well. Okay, I'll specify the hyperparameters as well. All right, so DT1 is equal to the decision tree regressor then DT1 dot fit x and y. Okay, so the decision tree regressor has been created. Then DT2 is again a decision tree regressor. I will specify max underscore depth. Previously, I defined a specific value. I'll give a different value now. Let's say maybe 8. Let's see how it works. Okay, and also I specify random state equal to and dt2 dot fit x comma y. So we have created, right, 2 different decision trees, one without specifying any hyperparameter, that is dt1, And the dt2, you can see that there is a one of the parameter I have used here, right? Maximum depth equal to. Okay. Fine. Let's do the plotting part now. That is quick axis equal to plt dot subplot. So I'm going to the subplots now. Again, the fig comma axis, right? Two parameters we are extracting from the plot here. So plt dot subplot, number of columns, right, equal to 2. And go to the fig size. Fig size equal to 10 comma 5 should work, I guess. Okay, let's see. And the y names, whatever we are specifying, they have to be shared by all of them. Okay, so what I do here is I specify share y. All right, share y equal to 2. Then plt dot set the current axis, SCA. Set the current axis is a function axis of 0 among your two axes which you have defined. Select the one with index 0 as the current axis. That's your x-axis. Okay, so go back to the plotting basics if you have any confusion over here, right? There you will get the complete details. Now you call the function. Okay, what is the function? That is a plot. What is the name? Plot regression predictions. Okay, this is my function. I have to pass, if you remember, I have to pass the functions one by one to this. Okay, so that is dt2, then x, then y. All right, it plots that. Okay, then I will set the current axis to a different one. Let's see. It's plt dot sca, set the current axis, right, to the next axis. That is axis of 1. All right, and plot regression predictions. Pass the other one. I think I already passed the one with the hyperparameters over there. So now I am supposed to pass the other one. So I'll call it as dt1. For this is the data x and this is the y. Okay. Okay, let's see what happens if I call this. Let's check out. Share y is equal to 3. That's error. Let me check. Reference to a Boolean object. Okay. That is the axis. Fine. Let me check. Yeah. Okay. Sorry. Well, my mistake. I didn't type it properly. So subplot is a function that is used in MATLAB. So I use MATLAB also many times. So normally when I type in Python, I type the MATLAB commands. In MATLAB, I type the Python commands. Sorry about that. That was my mistake. Okay, so it was a subplots. In Python, it is subplots. So over there, it was a subplot. That was a mistake, right? Other than that, right, everything is straightforward. So the first graph is actually the DT2, right? What is this DT2 represents? DT2 is actually, right, the prediction that happens through whenever we use the regression that is with the hyperparameters. Okay, that's first thing. And the second thing here is the next graph is without. Okay, so you can see a lot of changes that is happening over here, right? Whenever we are doing that without uh, the hyperparameters, but with the hyperparameters, right, you get a graph which is like this. So depends on our view that which is the most suitable one and which is the best one, right? That we can decide over here. Okay, so the first one we are plotting here is okay. Let me give a title over here so that I can give a name. Okay, let me try. PLT dot title max depth equal to 8. PLT dot title no restriction, so that we can see properly what is happening. Okay, which graph is what? If you want to visualize that, right, then I can give a title to that. Okay, so even the regression part, you can see that, right? The regression happens in such a way that, right, for an input data set, it is possible for given x parameters given, it is possible to predict the values of y, right? So if you try to compare the parameters such as what happened in the simple regression, such as the linear regression, and if you try to compare that with decision tree based regression, right, you can see the differences, right? Over there you are trying to define some of the parameters, and you will try to bring up the parameters over there, and you try to model the regression using the parameters. But here no parameters are used, right? That's one of the very fundamental differences. Okay, now, yeah, so it's a question time. Now I want you to look at some of the other drawbacks of this method. All right. So, okay, let me go back to the notes, and I'll try to write few more points over here. So the one of the point which we already have been, those are the issues related to the decision tree, right? I'll try to add up few more points. Okay, before that, let me change the screen. So as you can see, we have discussed and we have stopped after two different 2 points, right? So we have seen that these are the 2 points which actually uh, indicate the issues with the decision tree. Okay. Now let's go ahead. Let's move further. So the point number 3, which we can write is, normally whenever you see this kind of decision tree representation for the regression part, right? Normally, even if the tree is visible to you, but this tree provides lesser information on what is the relationship between the predictor and the target variable. Okay, what is the relationship, right? If you know that if you are using the parameters, you know the relationship, in the sense, in the form of an equation, you know that, okay, theta naught plus theta 1 times x1 plus theta 2 times x2, this is the relationship between the x and the y. We know over there in case of a regression, but that is not going to happen over here. So that is one of the limitation. All right, so I can write it provides lesser information on the relationship between the predictors in the form of right, the x variables, okay, and the target variable. So normally y equal to theta x plus c is the standard format, which actually relates in case of a linear model. But that is not going to happen over here, right? Is the first, sorry, is the third point which we are going to write under the issues related to this. Okay, and whenever the x, that is the data set containing the features, there is more variance, then the decision tree looks more biased towards that. Okay, so that's another point which you can write it as a issue. So point number 4, right? The decision tree is basically looks, it's biased towards the predictors, with predictors with a high value of the variance. So whenever that variance is high, right, right, the predicting those values are more frequent. Okay, so that's what we can see. Then one more, it is, all these are observed facts. Okay, so we cannot prove it by doing some maths now, but yes, you people, whoever was doing some research over this, right, they observed some issues and they tried to explore the reasons behind those issues, and they could identify all these points. All right. So the next point, point number 5, that's the fifth issue that we can observe is if you have some of the parameters which reside on the same line, we call it as a collinear. Okay, so collinear, collinear in the sense if you have 2 points and you can have a third point on the same line, it's actually a linearly dependent, right? So on the same line, they are dependent, they are present on the same line. The mathematical term used for that is the linear dependent. Okay, so in such cases, even that's true in case of in the vectors, right? If you remember, I have a vector in pointing one side, I have another vector pointing on the same side. In the sense, if you have a third vector in the same direction, you can try to write that third vector as a sum or difference of the first two vectors. So that's the concept, right? So if you have such data points, right, in your particular column, again the decision tree shows some issues related to that. Okay, so maybe the prediction or the prediction doesn't go so well, right? So again, so whenever people observe that particular point, they try to explore what's the reason behind it, and this is the reason which they found. Okay, so I'll write that also a point over here so that you can refer, right? So the decision tree can have some issues with highly collinear, COLLI, collinear predictors. So if they're most of them are present on the same line, means yes. Okay, it may not be able to judge that particular column's effect on your y. So one of the solution could be if that particular column is really not important to you, you can simply eliminate. All right, so that's one option, but depends upon how important is that particular column. All right, so how important is that particular column, we may have to see before we remove the complete column. Okay, so that's the fifth point. Then another one is that the decision tree normally expects huge number of data samples. Training, right? Training is it expects huge data set. Whenever you have lesser samples for the training, it shows its accuracy is very less and it shows a poor performance. Okay, so that's another point that we can add up here. The prediction accuracy is very less or very low, less or low when the number of data samples, is less. Okay, so it means again the training is not proper, only that's the reason. Most of the ML techniques will be will be having the same issue. Okay, so that's the one point. Then I can add another point, say I think this is what we already have discussed, but I don't think we have written that in this way. So you know that it is very sensitive to the data sample points. The points move by a small fraction, means the tree will change. Okay, this is what we have discussed. I'll write it in a different way. Okay, so the statement that I'm going to make now is okay, the decision trees can become unstable. What do you mean by unstable? Right? This implies the same thing that we have discussed. Okay, so that implies if you have small variations in the data samples, okay, might result in, or I'll write results in a completely different tree being generated. So the technical term used here is unstable. Okay, so means whenever you, what do you mean by stability, right? Whatever you do, the system should be stable. But unstable in the sense, whenever I change one of the parameter by a very small amount, system responses in a different way. So system generates a completely different what you call decision tree. Okay, so that's the difference, right? So the system is said to be unstable over here. Okay, right. Now one more point I would like to add here. Let us say we have a data set with the balanced data. Okay, if you remember, the balanced data is a particular data which may have any number of classes. For each of the class, the number of data samples remains same. I may have 5 classes. Each class has 100 data. So 100 plus next class 100, third class is also 100, fourth and fifth 100, 100. So totally 500 for 5 classes. Each class has 100 data. If that is the case, you would call it as a balanced data. Okay, but it's not necessary. You may not be able to collect the same number of elements, same number of data points for all the classes. Okay, so when I try to collect the mails corresponding to spam or not spam, maybe I got 10,000 mails which are not spam, just 100 mails which are spam. You see, right? There is a huge difference between one class, number of samples in a class, and number of samples in the second class, right? Well, first class I got 10,000, second class just 100 maybe. So you see a huge difference. So this kind of data set is what we call as the unbalanced data. So for balanced data, decision tree is going to work pretty much fine. Okay, all classes are treated equally. But if at all the data set is imbalanced, it's not balanced. Okay, for imbalanced data set, there is a tendency that decision tree makes biased decision. Okay, it will make a biased decision. So that's a problem. So to overcome that, always it is recommended that you use the balanced data set only. Okay, so I hope you understood what's the problem. All right, so let me try to write that in a sentence. For imbalanced data set, the decision tree makes biased classifications. right? So this implies, so before you fit the model, right, it is suggested to balance the data set. Okay, so before you fit, it is always recommended to fit the make the data set as a balanced data. So how can you do that? So for take an example. So we'll discuss about that. That will be the last topic for the day, right? How do you balance your data set? Anyway, all the points are over, but the major issues with the DT we already have discussed. Okay, so I want you to tell me, right? How do you balance? So one of the data, there is class 1, there is class 2, and class 3. So class 1 has, say this is the plot which has 1000 points. Okay, the class 2 has 500. Okay, and the class 3 has just say 300 points. This is a problem, right? You understood the problem. So I want you to suggest how can you make all of them equal. First point is that you will say that take 300 from all of them. Okay, take 300 from all of them. Yes, my data set is balanced, but the problem is that data set becomes too less. Correct? You are actually neglecting 700 data points from my first class. That's actually unnecessary. You are losing, because to collect the data set itself you have invested maybe a lot of time, money, right, resources, etc. You simply don't want to uh, neglect your data, right? There should be any other method. Yes, anybody, can you suggest any other method so that you can retain the 1000 as it is? What are the other possibilities is what is my question. Think about it, not a very difficult answer. No coding is required, because coding already performs our whatever we are going to discuss now. There are built-in methods to do that job. Okay, so please think about it, and once you get an answer, either put it in the chat box or tell me the answer. Anybody? So what is our ultimate goal? I have to have, if I have 1000 data points, correct, my intention is to split the 1000 data points into some ratio, like 80 to 20. So 80 will become the training data set, training plus validation, and the remaining 20 will be the testing. Okay. Right, now I want all the 3 classes to be in the same ratio, right? So I want to make this 500 whatever the 500 you see here, right? That 500 is what I want to become 1000. So can you simply repeat? Will there be any problem if I repeat my samples, right? So all the 500 samples which you have, you name it as class 2, class 2, class 2. I repeat them once again, right? 500 becomes 1000. Okay, maybe that's a solution, but is there any problem with it is my question. If I do that, will there be any problem? Will there be any issue? Okay, I'll give 2 minutes for you to think about it and give me an answer. Okay. Yes, anybody?
No ideas.
No
I
idea?
think this is linked. This is related for the before
Yeah.
previous classes, no sir?
Sorry?
This is related for the previous classes.
No, nothing to do with the previous class. Just analyze and answer. That's all. So I have first class 1000 samples, second class I have lesser samples. So, right, if I simply 500, I already have 500 points. I repeat them. So 500 becomes 1000. Every point is repeated. So 500 becomes 1000. So first class and the second class have the same number of points. Okay, so I wanted to make the number of samples same, right? First option was, if you look at this, what was the first option? First option was elimination, right? So simply make all of them as 300, 300, 300. That is one
Yes.
solution, but I lose my data, right? So that's not a suggested way. So the second option which I'm giving now is don't eliminate, simply repeat. So 500 plus 500 so that
500.
this becomes 1000. Okay. So my question was, will it cause any problem or it is okay? This is not going to cause any problem, right? Is my question. What do you think?
This cause the problems. When first class is thousands and second class is 500, 500 thousands. So then and class 3 is also constant in 300. 300.
Okay. So you are saying that class 3 also should be increased to 1000, right?
Oh, yes.
Okay. So let's repeat that. So 300, 300, 600 plus 300, 900 plus 300, 1200 I get, out of which the last 200 I remove. Okay. So that this becomes 1000. Okay, if I do this, right, all the classes are 1000, 1000, 1000. So I have 3000 data points now. Is there any problem? Is my question. Now the data set become balanced, right? So balanced data, each of the class came. Now my question was, is there any problem? All are same, right? So this is what we wanted, correct?
Yes.
This is what we wanted, right? So we got what we actually were expecting, right? And since this happened, right, now you see that basically there is no problem, right? Our basic issue which we had earlier, right, is not there. Okay, so this is one solution. Whenever you have a huge number of samples in one of the classes and very less number of samples in other classes, you have to perform a data balancing. Okay, and the balancing should happen in such a way that you repeat, right? Whichever classes you have, whatever classes you find lesser number of samples, you need to copy them again and again so that, right, all the samples are equal, right? You have to make it equal like this. Now, for the last class, you see that you have 1200. If you remove the 200 from the top, no issues, because those samples are already there in the class 3 data. They are repeated. Okay, so repetition, if you remove, no problem. But for the first example which I took, right? So there we had only one solution saying that you remove the 700 samples from your 1000, right? So whenever I try to do something like this, right? So these 700 samples were not at all repeated. They're coming for the first time. They cannot remove them. Okay, so that is the issue. So unbalanced or imbalanced data, you have some problem. You repeat the classes which have lesser number of samples to make them equal, right? So that the complete data set becomes balanced, right? Has no problem. That is absolutely fine. Okay?
Yes.
All right. Okay, so do we have any other doubt? Anything you want to discuss, right? Please go ahead. So the decision tree, the theory part as well as its corresponding the coding part we have completed. Okay, and in the upcoming session that is tomorrow, we'll be starting with the next algorithm that is called as the random forest. So random forest is directly related to this. Okay, so since it is in that way, we'll be directly jumping into the random forest. We use the concept we have discussed in the decision tree. We extend that so that we go to the random forest. So tree is single, forest is multiple trees. So you should be able to relate what is studied in tree and how can you extend that to a forest. Okay, only that is the difference, right? So it's very interesting that how a tree is extended to the forest concept, right? And randomly you choose trees from the forest. Okay, so that's how the random forest is going to work. I'm just trying to give a big picture. All right. So do we have any other doubt? Anything you want to discuss? Please go ahead. Anybody?
Today participants is some less in 10 participants only.
Sorry.
Today participants is only 10.
Yeah, I can see very less today.
Yeah.
Okay, initially there were I saw 17 once, but later on they dropped. That's okay.
Yes.
Okay. Anyway, people can watch this video later and they can understand. All right. So absolutely fine. So if you have any doubt, then please ask. Please go ahead. Okay, so that brings us to the end of the session. All right, and I hope the session is useful, and right, I appreciate your efforts in attending the session.